We are all familiar with how refracting telescopes work. An objective lens gathers and bends the light into focus, and an eyepiece, a small lens, brings the object from the focus and magnifies it to the size of your pupil. Without the eyepiece, we lose the ability to magnify from the focus, and thus proper images cannot form in our eyes. However, with a little ingenuity, we should be able to use a small pinhole to achieve the same result. A pinhole in this case acts on the same principles as the camera Obscura, a precursor to the pinhole camera. A camera Obscura device consists of a box, tent, or room with a small hole in one side. Light from an external scene passes through the hole and strikes the surface inside, where the scene is reproduced, inverted, and reversed, but with color and perspective preserved. Essentially, by not letting all the light pass through, an image is formed through the remaining rays going through the hole. In our experiment, essentially the same thing is happening, but on a much smaller scale. Without a magnifying eyepiece, we are unable to see anything out of a telescope. Too much light is still entering our retina. We will use an iPhone 7's camera as a substitute for an eye. It can focus excess light and change its field of views and depths to an extent, similar to our eyes. The pinhole now effectively limits the amount of light coming into the sensor of the phone, which is in this case the retina, and now we are able to see an image. The magnifying front lens obviously magnifies the image, and now instead of an eyepiece, the pinhole gives us the same but darker image. There are some problems with our image, however. To the sides, we can see black spots that form in a circle like the ones we see in an old film. This is due to vignetting, as is our case. Mechanical vignetting occurs when light beams emanating from an object points are located off the axis and they are partially blocked. In our case, they are blocked by the pinhole. Light falls off with the inverse square of the distance from the source. This implies the further an image is from the center, the more it falls off, causing vignetting. Furthermore, due to our inability to form a perfectly round pinhole, we do see some interference due to it. Excess light and lack of light in other places also causes light and dark spots on the image. However, this doesn't actually change our findings. Now that we have established that it is possible to make a telescope with a single lens, we must find out the factors that change it. Obviously, a larger lens means more magnification. The light is displaced by a larger angle. But what happens when we change the size of the hole? Theoretically, if we make the hole bigger, we should see more of the image due to less light being obstructed, and the image should also be brighter, due to more of the image now being available for us to see. The magnification would thusly seem less because there is more to see from the pinhole, and vice versa. This is exactly what we saw. From these pictures, the smaller pinhole shows less of the image darker, while the bigger pinhole shows more of the image brighter, and thus it feels to us that the small pinhole is magnifying to a larger degree. Smaller pinhole means more magnification and less light, and larger pinhole means less magnification and more light. In conclusion, it is possible to build a telescope with a single lens. Using the fundamentals of the inverse square law and the properties of pinhole imaging, we successfully hypothesize what would happen when the lens and the hole is changed.